So today we are going to begin optimization. Okay, we are in the chapter or the unit um, where we're talking about the application of derivatives. Okay, so I want you to keep that in mind. Do not write anything down right now. I want you to read through this problem. Just read through it. We want our volume to be as large as possible. Is there any way we can relate this to calculus? If we're trying to get something to be as large as possible.
Oh, it's something to do with like the volume or something.
What we could probably do is to give volume expansion and find a relative maximum.
Oh, maximum. We did all this work with maximums and minimums, right? So if we, did you see that?
Yeah.
Cool.
That was creepy. Okay.
Pretty cool.
My board just lit up.
I think it's Z-bars on there. Yeah. The metal one's like probably here.
Oh, probably. Yeah. So if we are presented with a problem where they're asking us to optimize something, make something as big as possible, or make something as small as possible, we have this first derivative that can help us find minimums and maximums of a function, right? You guys enjoy? Okay. So, don't write this down because I'm going to give you a note sheet. That way you don't have to write down my entire word problem. Okay? Here are the directions, or here are the things that we need to think about when we are presented with an optimization problem. Okay? First of all, we're going to need to draw a diagram. Okay? That should not surprise you at all. Okay? You'll want to determine the equations that you'll be needing. So for sure there will be a primary equation, and this will be related to whatever you are optimizing. Okay? So if it's asking for you to make the volume as large as possible, your primary equation will be the volume equation. Okay? If they're asking for you to minimize perimeter, then your primary equation will be the perimeter. Okay? Now sometimes they don't give us enough information. Okay, we can't take a derivative we can. But to use the first derivative test, we need our function to be in terms of one variable, so we can take the derivative and find a minimum and maximum. Okay? So it's possible that we're going to have to eliminate a variable using a secondary equation. So if we have one equation with x and y and a second equation with x and y, we can use that second equation to help us rewrite the first in terms of just x. Yes?
Is this like related rates?
It is not related rates. Okay, there's a very important difference between optimization and related rates, and that's something that we're going to work with on Monday. Okay, related rates would be more, our volume is decreasing at this rate, our radius is increasing at this rate. Here we have a figure that's not changing, but we're trying to optimize something. Okay. Okay, I know you don't always like the word domain, but we need to think about the feasible domain. Okay, if we have a box, is -2 an appropriate side length? No. Okay. And then we're going to use the first derivative to find the min and max. Okay. Really, once you get your equation written, it's the first derivative test, which you guys all rocked a week and a half ago. Okay, 2 weeks ago. I don't even know anymore. But we know how to do the first derivative test. You've been doing it over and over and over with your curve sketching. All right. So let's go back to job number 1. This is what's on your worksheet, correct? Okay. So the first thing we should do is
Draw a sheet.
what do we know about this sheet? 12 by 12. And what are we doing to it?
Cutting squares and making the cube.
We're going to cut congruent squares out of this. Right?
Is it gonna be,
How's that
gonna be a
make it
box
in
with
the
an
box?
open top, or is it just gonna be open? That's an open top. Okay.
It's a box with an open top. Because what we're going to do, we're going to cut these squares and we're going to fold it up. Right? So we want to know how big to cut these squares. So I'm going to label these squares as x by x. That would be a square, right? So our primary equation needs to relate to whatever we're optimizing. So what are we trying to do? Are we trying to minimize or maximize? We are trying to maximize the volume. So I'm just going to make a note to myself that we're looking for a maximum of volume. Okay, so we need to write a volume equation. If we fold up these flaps, okay, what would the volume of our open box be?
12 minus 2x squared times x.
Okay. When we fold this up, we really only have this length right here as our side. You see that?
You have a box
No. I don't have a square piece of paper, do I? Okay. Hold on. Square. Now, these aren't going to be excellent because I'm not measuring.
Forgot to do the first derivative.
Just making it. Okay, so this is what we have, right? And we're going to fold these to make a box.
That's not.
It's an open top box.
Why not have some ambition to create slits on the sides so that we could use the sides that you would have cut off as board compartments?
Well, we're trying to use the least amount of material. Like here we're using all of our material. We're not cutting. Well, that's not true.
I feel like this employee would want to make these boxes.
Because everything's just gonna fall open.
Wait, do you have to make a slightly?
Work blocks are, we make a whole bunch of designs.
Thank you. Thank you. Okay.
Come on.
So how do we find the volume?
It's just for
Each side is what is this length right here?
12 minus x.
12 minus 2x. This length.
Squared.
12 minus 2x times what's the height of our box?
X. Wait, what side did you point to after?
Okay. So length times width times height. Okay. Now, in this example, it turns out that we are in terms of one variable, so we do not need a secondary equation. Awesome. Okay. So if we are going to do the first derivative test with this, what do you want to do?
Probably take the derivative first, right?
Put it together.
Okay.
Square it and then multiply by x.
Do you want to multiply everything out so we just have to do the power rule for our derivative?
Yes.
Okay.
Why don't we just do two?
So I'd be ready to multiply three.
It's a product, we can do product rule. Would you like to do product rule?
No.
Yeah.
No.
And look at classes that agree.
Multiply it out so we can do.
I agree with the problem.
The product rule.
You mean power rule.
How many for power rule? How many for
Rule.
product rule?
Three.
You didn't
I
even
know.
go for the right thing. So, okay. This is 144 minus 48x plus 4x squared times x. So our volume is 144x minus 48x squared plus 4x cubed. What is the derivative of our volume?
144 minus 48.
Minus what?
96.
There we go. Plus?
12x.
Great. Okay, now, before we go much further, there was one thing that I skipped over. What did we not talk about before we took the derivative?
The domain.
We didn't talk about the domain.
Well, it's not truthful.
X's can't be negative.
X's can't be negative, and we probably can't be 0. So x needs to be bigger than 0.
Less than 12.
I agree with less than 12. Ooh, why 6?
You cut 2 squares out.
Because if we're cutting 4 squares out, if they're 6 by 6, that would be the entire box, right? Exactly, which is why it's not a part of our domain. Okay. Thank you, Nathan. Okay. So back to our derivative. What are we doing with? Why do we take the derivative? Okay, we need to find our critical point. So what should we do with our derivative?
First,
Divided by 12.
back out of 12.
Set it equal to 0.
First, we would set it equal to 0. Then we could factor out a 12. Okay, so we can divide that 12 off. I'm going to rewrite this: x squared minus 8x plus 12.
Negative 2 or x minus 6x.
So we have critical points of 6 and 2.
But 6 isn't working.
Okay, so 6 isn't working. So Zach already knows that this answer is going to be 2. Okay. However, you need to show me that this is a maximum. Okay, we are maximizing our volume, so I need to see evidence that you tested it to be a maximum. Okay, is it possible that sometimes you could screw up on your algebra? It is possible. So, if you find a critical point and it doesn't change sign of your first derivative, then it's possible you made a mistake and you need to go back. So you always need to check it to make sure that you actually do have a maximum. So 2 and 6 are our critical points, but we don't have to worry about 6. We just have to worry about what's happening on the left and right of 2. Yes, sir.
If you want to, like, there's obviously going to be like a maximum volume you can have and a minimum volume you can have. But if you only get one critical point, then you want to just review, only have a minimum, like with first you get max, but you only have one point. So, you know kind of what I'm saying?
Well,
Because like right now, we only have one critical point. So what if we're looking for the max, but that two happen to be the minimum?
okay. It's possible that you're not always going to have a minimum and a maximum.
But like,
What if we
for
did this
the box,
instead of
there's
finding
obviously like the smallest way you can do it, and there's like the biggest way you can do it.
The smallest one would be 5.9.
The smallest way is 6.
Like, we have a minimum at 6, right?
Like, that's bare minimum.
So, which is really a volume of 0, right?
So realistically, it's
So,
not-
I mean,
mathematically,
that would be your minimum. Mathematically, that's the minimum. Okay. Does that make sense?
Yeah.
Okay. We plug in 0, we get positive. We plug in 3, we get obviously. Test it. Okay, so we have a max when x equals 2. Okay, so make sure we go back and answer the question. How large should the cut squares be? They should be 2 by 2 inches. You did guess that.
Well, first I thought it was gonna be a closed box, but I saw that it was 6-sided, so I couldn't tell.
Because they'll keep it closed. Now,
We don't have to like, so, because of the max,
Yeah, do you have to justify?
probably not. However, if I don't see evidence that you tested for a max or a min, you will not get full credit for your problem. Also, make sure you answer the question. Okay. All right. Would you like to do, let's go to our paper products.
Paper products.
why is everything with cardboard and paper?
Paper products plus.
How much do you
Thank you.
Okay, so read your problem.
Maybe.
really big important chocolate bar, you can get on.
Okay, what are we working with?
Minimum paper.
We have a piece of paper. Okay. And this paper has, okay, and we have margins, right? How big are our margins? So 1 inch on our side and 1.5 inches top and bottom. Oh, I didn't, whatever. Okay. So we want to know the dimensions of our page.
It says 44 square inches of print. Is that including margins or not?
No, that's the inside because.
That would be the inside, okay? So this is gonna be my suggestion. Since we know the square inches of print, okay? We need, I'm gonna call this X and this Y. that will help with our square inches of print. Okay. So let's talk about our primary and secondary equations. I just wrote two different variables, so we're going to have two different equations here. Okay. What are we trying to optimize?
Minimize.
Okay. We want to use the least amount of paper as possible, right? Okay. So that is talking about area, right? The area of our paper. Okay. What is the area of our paper? X plus 2
Times y plus 3.
times y plus 3. And we are looking for a minimum. Okay. Now, we know that there's 24 square inches of print. So we're going to use that for our secondary equation. It's going to help us. Okay? So what does that mean if we have 24 square inches of print? Okay.
Oh, no.
Let's talk about our domain. When we have written two different variables.
Oh,
Because we can't take this derivative yet. Okay? To do the first derivative test, we have to take an explicit derivative.
Will we ever have to write tertiary equations?
What?
Because we have to write tertiary equations if we had.
No. We're just gonna stick with primary and secondary.
So you can't do it if you want the X.
Well, we can't do the first derivative test with that.
Solve for one variable.
Okay? Well, first of all, I want to talk about the domain. What connects B? Look at the picture. What connects B?
Anything but 0.
Anything but 2. Or it has to be above 2. It has to be above 2.
It has to be greater than 0.
It has to be greater than
0 and less than
less
12.
than 22.
Less than 12.
This just has to be, you know, it's not shared.
Greater than 0 and less than 12.
Where are you getting 12 from?
Since the minimum would be, doesn't have to be greater than 2.
Yeah,
Greater than 2?
yeah, because we actually have at least 2 inches of margin.
Well, yeah, but X doesn't
Yeah, it
take
doesn't-
into account.
So it has to be
Oh,
greater
It just has to be
than
0.
0 and then 12.
It has to be greater than
22.
Well, you have to have those margins, so you do 3 times 2.
But I think X must be less.
That could be 24, because Y could be like 1, and then you still get 24 square inches, right?
because, X plus 2,
Or not. 6, yeah.
24, I think.
X plus 2 equals. And if y is 0.
You're gonna go to your secondary equation if it can't be greater than 24, right?
You can do it, you can be. Because
Then it's
if you
like-
do like half a y.
she's just testing our character.
Okay, so for right now, for sure, we know X has to be greater than 0.
So does Y.
And so does Y. Okay? So let's maybe leave it there and maybe come back. Okay? And maybe it won't matter later. Okay? For right now, we'll leave it. Okay. So we can't take this derivative yet. We need to write this in terms of just X. Oh, good thing we have that secondary equation. Y equals 24 over X. And now we can plug that in so that our function is just in terms of X. So we have A is x plus 2 times 24 over x plus 3.
Right, this 24 is
You could. Let's go ahead and FOIL this out first.
Yeah.
Okay, because you don't, I would not suggest doing a product rule here. I would suggest, let's just write it out. Okay, so our area, what's x times 24 over x?
24.
Plus x times 3 plus 2 times 24 over x plus 6. So what we have is 30 plus 3x plus 48 over x. Right? Okay. If you want to write it as x to the negative first, that's fine. Some of us by now can think about that in our head. Right? Okay. So now what do we do with this? We take the derivative. Derivative of 30.
0.
Yay. Derivative of 3x.
30.
Okay. Derivative of 48x to the negative first. Negative 48x to the negative 2. Okay. What do we do with our derivative? We need to know where this is 0 and undefined. Therefore, we need to make this. Okay. Not hard, right? Our common denominator needs to be x squared. So 3x squared minus 48 all over x squared. Okay. So where is our derivative undefined?
0.
We have critical points at x equals 0. And then what would make our numerator 0? We would have to factor out a 3. 15? Okay. So plus or minus 4? Okay. So we have critical points of plus or minus 4 and 0.
Well, it has to be 4 because it can't be 0. No, it can be negative.
Okay, it's negative 4 in the domain.
No.
It's 0 in the domain.
No.
So we better test 4. Okay, but we need to account for there is a critical point at 0. So when you plug into test, you need to pick a number where? Between 0 and 4. Okay, so if we choose 1, what does that make our derivative? Negative. If we choose 5, that makes our derivative positive. Okay. So we have a minimum when x equals 4. Okay. Now we had two variables. If x is 4, let's come back up to our secondary equation. What does that mean about y? Y is 6. Okay. Now, that hasn't answered our question though. Our question, what should the dimensions of the page be?
The primary equation.
Okay, so the dimensions of our page, 6 inches by 9 inches. Okay. The only thing really new is setting up the primary and secondary equation with your picture. Everything else is the first derivative test, which you've done over and over and over again. Okay. One more problem.
Grable did 4 problems with his kids, so you can
How about we compare test scores one day and see who's the better teacher?
That's not fair.
That's not.
Yeah.
We have different kids, we can't compare.
Or then have people like teach us even.
I'm not giving you guys up for an experiment. I like you guys. I don't want Grable to have you.
Are you passing the
What?
test? You passed the
So there's a
test.
few of us who'd rather having Greebles or you'd send over there, right?
You're saying you don't want to have me? Is that what
I'm
you
saying, I'm
said?
sure you would want to send
Oh.
a few of us over there.
Not every day. Okay, so what's happening?
You decided to go
Let's
from
go
making
one
boxes
way
to
to what the
Shooting Russian missiles out of the sky.
Yeah, that's about right, Carl.
I really like this question.
Okay, so we have a function, we have a parabola, where we are trying to do what with that point?
One of the closest ones I think
So we are trying to, we're trying to minimize, okay. Four minus x squared. And we want to come closest to the point 0, 2. Okay. So what are we minimizing? Distance. And our distance, how do we find distance?
Well, there's no way to find it. You can wait till we come to this. Wait, no.
We don't.
Okay, so this is the point 0, 2, and we're talking about a point on this xy. We want to know which point is the closest on that parabola.
the 0 minus.
Can we
just triangle?
X minus 0 squared and y minus 2 squared. Yes, our distance.
Wait, once you have 2 points that are exactly the same distance from that point.
Yes. So Brady just said we might get 2 answers.
You can't travel backwards.
Yes, you can.
What? We don't know. We don't know.
Yeah, but it'll be close.
But it's like going this way and then it curves over.
Well, like we shoot it and then it comes back out.
Can we just estimate, so like 1 for reproduction and -1?
We're not gonna estimate. This, okay, seriously, people, this is probably one of the easier problems we're gonna do today.
But it's the last one, so it's always on this.
What's our secondary equation? What's our secondary equation? Good.
Y equals
X, Y equals.
You would have to think about it. Okay. So y equals 4 minus x squared.
That's fine.
Oh, wait a second.
Oh, this one's
So
actually-
here we have x squared, because that's x minus 0 squared. And we know y is 4 minus x squared. So our distance is x squared plus 2 minus x squared.
X squared.
Squared, sorry. Squared. Which is 4 minus 4x plus x squared. Just some nice algebra here. So we have 2x. Thank you. Some nice algebra that Mrs. Holman is. Okay. So we have x to the fourth minus 3x squared plus 4. Now, I want you to think about this. Okay, right now we need to take the derivative. And some of you are saying, I don't really want to. Why?
They've got a big
Because it's a
radical.
square root. Okay, now, I want you to think about this. If we're finding the minimum of a radical, we're finding the minimum,
X cannot be one.
then if I just find the minimum of what's underneath, when I put it in the radical, wouldn't it still be the minimum?
Yeah.
Okay, if I take away the radical and find the minimum, then when I put that in the radical, wouldn't it still be the minimum?
Yeah.
Maybe.
Yeah, I said it's a 0, if you square root 0, then it's 0.
If you square that original function.
Okay, so if I find our minimum without the square root and it's 4, then that just means our minimum with the square root is 2. Like it's still, like the square root isn't going to change the fact that we have a minimum, right? Or maximum or whatever.
It's just
We didn't
Okay.
remember to apply it.
So then once you say it's just like d squared equals.
So what we can do instead is we can just write this as capital D. We'll just rename it as a polynomial. That way, the derivative is nicer. Okay? Because if we're minimizing the square root, then what underneath of the square root is going to be minimized.
But
Okay.
when you do square root derivatives, they end up being fractions.
Right. And, but we would have to do the chain rule, right? And so this is basically just the chain rule that we're going to do. Okay? So,
Whoa.
I know, it keeps
It
doing
keeps
that.
doing that, so you're
No.
fine.
I know, I don't think it's supposed to do that. So what is the
Things right.
It's the need.
It's
Is it turned
Two
off?
bucks, get your cyborg leg or control.
It's slide over.
Look at the lights.
Sorry, Aaron Davis.
Can you hear you? Got that thing on?
It's actually Aaron Davis. Yeah, think about it.
Oh my gosh.
He's actually a girl.
Okay, we're gonna have to finish this problem up here.
Oh, you can't see it.
It'll be okay. So our derivative is what?
4x cubed minus 6x. So much enthusiasm.
So where this is 0, let's see, we can factor out a 2x. And left over is 2x minus 3.
2x squared.
Oh.
Ah,
So our critical points are at 0 and plus or minus
3/2.
radical 3/2.
so
Now, we're talking about, can't even go back.
Parabola.
We're talking about a parabola, okay? Are all of these points okay? Yeah. So, our sign chart. To the left of radical 3/2. So like -2. Does -2 make that positive or negative?
Wait, is it, are we doing the little b1 or the big?
Well, we only took the derivative of the big.
makes it negative.
Makes it negative? How about in between here?
Positive.
Are you positive?
In between here
Negative.
and here.
Positive.
Who was talking?
That's Z-Buzz.
World train.
Z-Buzz is like.
Excellent. So what were we even doing? We were
Finding the closest point.
closest. We were minimizing, right? So here we have a minimum, and here we have a minimum. Hey, didn't Brady say we could have two answers because it's a parabola of symmetry because it's on the axis of symmetry? Okay.
Good job, Brady.
So
Thanks.
we have a minimum when x is negative radical 3/2 and when x is positive radical 3/2.
Jack, keep trying.
Okay, good.
Wait, so how come that turns out to be like not like a minimum on the graph? Like, cause you know how it says
Oh, you
minimum when
minimize
you,
the distance.
first, I thought like, it was the function of like.
No, not the function, we're minimizing distance. Very good. Okay, so when we plug in plus or minus radical 3/2, we get 4 minus 3/2, which is
Where are we going?
3.5. No, 2.5. So 5 halves.
yes.
Yeah, so I was with that 1, 3-ish estimate.
Yeah.
Wait, did we put that into the,
Yes.
so did we put that into the
To
equation?
the secondary, y equals 4 minus x squared.
Yeah.
When you have two different variables, you want to go back to the secondary equation to figure out the second. Okay? So your homework, page 220, is up there. Number 2, B and C only. Don't do the chart thing, just do it regular, normal, okay? And then you have 3, 9, 11, 15, 19, 22, and 29. The first one is number 2, letters B and C only. Don't do the chart thing. Don't do it.
We'll do it then.